Hello and welcome to this presentation on linked list. Previously we saw a list container that used a dynamic or expandable array implementation. That was some of the work that we had done before. This week we want to look at how to create a slightly different version of a list. It still has the same capability, but the underlying mechanics, the underlying storage features are very different. Before we get to actual linked list, let's do a review of pointers. Pointers are somewhat unique in C and C++, so we'll do a short review of that. All data and code in memory has an address. So when you have a block of memory that's reserved for your program, the data goes somewhere in that memory, and its location in memory is an address. So the address is the location where things are stored, and a pointer is a variable that can store an address. So in C++, we can define a pointer variable by using a data type followed by an asterisk. So here you can see the variable p is not an integer, but a pointer to an integer. That's what this asterisk means. So p is an integer pointer. X and y are integers, and they store the values 7 and 18 respectively. So over here in the diagram, we have x that has the value 7, and y has the value 18. And what I've done is I've put a number on the outside of the box, very similar to the number you might see on the outside of a mailbox, that would represent the address. So the address of x in this case is 104, and the address of y is 108. And that's the location, like the address on the outside of a mailbox, that's the location in memory of where those variables x and y are. Now the values 104, 108, I just made them up. They're fictitious addresses. We don't get to set those as programmers. We'll see how we can view them later, but right now I just created these fictitious values. So really important to realize that the value of x is 7. The address of x is 104 in this made-up example. The value of y is 18. The address of y is 108 in this made-up example. We can access a variable's address by using the address operator or putting an ampersand in front of the variable name. So this line here, ampersand x, means take the address of x, get us the address of x, and then the address of x is stored in the variable p, which is an integer pointer. So what happens then is we get the address of x, which is 104, and we store it in the variable p, so that's why p has this value 104. So this is the interesting part here. P is a pointer, and it's pointing to or referring to the variable x, and that's why we use this arrow here. Normally, when we draw these diagrams, we will just draw the arrow, and we won't use the numbers 104 or 108 because they're fictitious numbers and we don't know what they are in general. So once again, ampersand x means get not the value of x, but the address of x, and put that value in p. So now p points to or refers to the variable x. And we could have said p equal ampersand y, in which case we'd have p pointing to y instead of x. So just a review of pointers, addresses, and the address operator. Most debuggers will show you, you can see a variable's address in the watch window, and they're often shown in hexadecimal values. There's some advantages of doing that, but they can be challenging to work with because hexadecimal values, here's an array, and the array has 4 things in it. And the array name A1 has this hexadecimal address. So that's the address of the first item of the array in memory. So you can see that if I take the address of A1 sub 0, I get the same value as A1. So A1, the array name, is essentially storing the address of the starting point of the array. Notice that the address of A1 sub 2 is slightly different. It gives us the value 6. Remember, zero-based indexing, so 0, 1, 2 gives us this location where the 6 is stored. So notice here that this address of the first position ends in E4, and the address of the 6 ends in EC. And the reason for that is if you start at the first location and move one integer, that's 4 bytes. So if we add 4 bytes to E4, we would get E8. So if I start out with E4 and I add 4 bytes to it, I get E8. And then if I add 4 more bytes to it, I would get E12. But in hexadecimal, 12 is written as ABC, 10, 11, 12, so it's EC. Hex is base 16, and values that are above 9 use the letters A through F. So that's how the math works out on those hexadecimal values. Again, they can be challenging to work with, but there are some advantages because they're base 16 and because memory often uses powers of 2, so there's some advantage of working with hexadecimal values. That's why when we use the diagrams we saw in the previous example and future examples, when you use the diagrams of working with pointers, you often see the arrow rather than an actual number for the address. We can access the contents of a memory location through a pointer using what's called the dereference operator. So once again, we have our example where the value of x is set to 7 initially, and then we take the address of x, which is this 104, and store it in an integer pointer p. So now p points to or refers to x. We can change the value of x. Obviously, we've seen this. You just write x equals 24, whatever you want your value to be. Okay. If we wanted to access this storage location through the pointer p, we would use this dereference operator. And that's just putting an asterisk in front of p. So we say star p, which says go to the location that's pointed to by p. So star p is not this location, but star p is dereferencing the pointer, going to the location referenced by p, and that's this. So we're going to take the 24, and we're not going to store it in p, we're going to store it in star p, which is dereferencing this pointer. So the 24 actually goes here. So 7 is no longer stored in x, but now x has the value of 24 when this code finishes running. So this is using what's called the dereference operator to access the contents of a memory location through a pointer. Last time we were able to create arrays dynamically, expandable arrays or dynamic array with the new and delete operators, and here's some examples of that. In the first case, I create an integer pointer and set it equal to a new integer, just one new integer, and that's this situation here. The new integer doesn't have a name because it's been allocated dynamically, but we will be able to access it through the pointer p as long as we store the address that's returned by new in the pointer p, so that p refers to this, and if we wanted to put a value in there, we would write star p equals some number, and then that means the 4 would go in here. Star p equals that value. We can also allocate an array like we saw last week. So here's an array. We've got an array of size 4. So I say new int array and store it in the pointer p array. So now this array is dynamically allocated. It doesn't have a name, but we access it through PArray, and we can use the subscripting, the array subscripting notation to access each of the elements. So in this case, we have a loop that goes from 0 to the size of the array, and we set the contents of the array equal to the loop variable times 3. So 0 times 3 is 0, 1 times 3 is 3, 2 times 3 is 6, and so on. Those will be the contents of the array. When we're finished with these memory locations that we've allocated dynamically, in order to avoid a memory leak, it's an important step to free up that dynamically allocated memory, and there's two different versions of it. The first version is we use delete with just a variable name p, and that frees up a single object. In this case, we just have a single integer that we're going to free up. The second version is we use delete with the square brackets behind it, and that version indicates that we're freeing up an array that's been allocated in this way. And so the second version will free up all of these integers because we have that square bracket behind it. So it's important to use the appropriate version of the delete operation, whether you're deleting a single object or deleting multiple objects that you've allocated as an array. So far, again, this is just a review of pointers and addresses, dereferencing objects, and memory allocation with new and delete. Now we start to get to the linked list content. And one of the really interesting things that you're able to do is to create an object that has a pointer type that can store an address to the same type of object. That sounds confusing. Let's go over it. Here we create a struct we call node. So a node in a data structure is kind of a common term. It's just one object that holds data in a data structure. So here we create a struct called node, and the node is going to have two parts, two pieces of data. The first piece of information is the actual data that we want to store, a number. The second piece of information is a pointer to another node. So this is an interesting concept. We have an object called node, and within that object we can store a pointer, the address of another object of the same type. So this is an interesting concept. Here's what it looks like in a diagram. I have a node here, and the node has a data. In this case, the value is 8, so there's the data part. And the node has a pointer to another node. In this case, it happens to be null. Later on, we'll take more advantage of it, but in this case, it just happens to be null. So those are the two pieces of information that are in node. Here's some code that uses a node and sets up this diagram. So we create a node pointer called pFirst. So the first item in the list, pointer to the first item, and we set that equal to a new node. So that creates this situation here without any data in it. pFirst points to a new node. We don't have any data in it just yet. The next step is store 8 in the data part of the first node. Notice this syntax. We can access, so typically with a structure, if you had a node, you say you had a node in or something, you would access the data by saying node.data. Right? In this particular case, we don't have a node in, we have a node pointer, pFirst. And you can't say pFirst.data, that's not legal syntax. What you can do is access the data member or the pNext member of the node through a node pointer by using this pointer member operator. And that pointer member operator looks like this. It's a hyphen followed by a greater than sign. So it kind of looks like an arrow. So we notice we use the pointer member operator, arrow, just like in our diagram, we have arrow. And what that arrow means is go to the data part of thing that's pointed to by P first. So the thing that's pointed to by P first is this node, and we want to access the data part of it. So we take 8 and store it in the data part of P first. So the 8 goes here. We take null and store it in the next part of P first, so the null goes here. So this is how we access data members of an object through a pointer to that object, is using this pointer member operator. And also don't forget, when you no longer need that object, be sure to free it up. We use this version of the delete because it's a single object. So now that we can have objects that can store addresses of other objects, we can start to connect these different objects in a variety of ways that are limited only by our imagination. So let's see what a linked list looks like. I've got an interesting picture up here. If you remember kids' toy they called Barrel of Monkeys, and the little toy plastic monkeys have arms that are in the shape of hooks, and you can hook them together or link them together, and this is what we're going to do in a linked list. Another good analogy is think of as hooking up trains. So you had toy trains as a kid and you used to hook them up together. This is a similar idea of what we're going to do in a linked list. Each node is a car and a train, or each node is a monkey in a list of a link of monkeys here. So again, we've got the same node definition. It has two parts to it, a data, in this case storing just an integer. It could be anything, string, double, a collection of things. And the other key part of this node is it has a pointer, so it can store the address of another node. So now we can actually create a list of these nodes that are linked up like cars in a train. Here's some code that does this. I make a new node and set it equal to P first. So P first is going to point to this new node. We store the 8 there. And now in the next, instead of storing a null, we store another new node. So now next is pointing to another new node. Unfortunately, the syntax gets a little messy. In order to access the data part of this second new node, I've got to follow two pointers. I've got to go P first, and then P next, and then access data. So I've got to do P first, excuse me, wrong line, P first, P next, access data, and store the 15 there. And notice we use this pointer member operator twice because I'm accessing this data through two different pointers. P first, P next, and then accessing data. So these diagrams are really useful, almost crucial whenever you work with data structures. Whenever I'm writing code for data structures, I always have some scrap paper beside me, and I'm always drawing these little diagrams to make sure that the code is doing what I want it to do. The next item is we're going to set that last P next to null. So we say P first, access P next, and another P next, and we set that to null. So P first, P next, access this P next, and set it equal to a null value. So what's happened here is we actually have a linked list. It's not very large. We only have 2 items in this linked list. The first item is storing an 8 for us. The second item is storing 15. And notice that we can use the null value as a sentinel value, similar to an end of file value in a data file. We can use this null value to signify, oh, that this is the last thing in the list, don't go any further. Deleting this particular list can be a little bit challenging, but we'll look at some other examples in a little bit. Before we get to some other examples, we want to look at traversal. How might we traverse this list or step through the different elements in the list and print them out or count them or compute an average or find the minimum? Very common that you want to be able to traverse or step through each value in a container. Here's how you would do that. Again, the data structure is the same. Our list is a little bit longer now. We've got 3 items in our list. and we still have this sentinel value that marks the end of the list. So here's an interesting for loop that does not use an index like you're used to in arrays, but instead uses pointers. I call this pointer P Walker. So P Walker is going to be P first. So my P Walker is going to point to the same thing that P first points to. As long as P Walker is not null, well, it's not null, it's pointing to this thing, I'm going to print out the data. So the first thing I would print out would be the 8, because that's what it pointed to first. After we've done this, when we do the update part of the loop, this is interesting. We say P Walker equals P Walker next. So this is no longer valid. We set P Walker equal to P Walker next, which points to this guy. So now our P Walker variable is pointing to the second object in the list. So this is an interesting way of updating this pointer variable, this temporary pointer variable that's going to traverse or step through the list. So now we're pointing to the second item in the list, and as long as that P Walker is not null, and it's not null, it's pointing to the second thing, then we're going to print out its data, and so we'll get the 15 printed out the second time. The next time we do an update, P Walker is P Walker next, so P Walker was pointing to this. P Walker next now points to this one. So P Walker gets updated to point to the last item in the list. It's not null, it's pointing to a valid node. We print out its data, which will be a 3, and we update P Walker one more time. So P Walker was pointing to this last item, and now when we say P Walker next, we do get a null value. So P Walker is now going to have a null value in it. And when we do this test, P Walker not equal null, it fails and the loop ends. So this is an interesting way of stepping through or traversing a list, and maybe unique, a new way of using a for loop that doesn't have any kind of count associated with it. Instead, it's using addresses and a sentinel value. So now that we've studied a couple different uses of pointers to create linked lists and traverse them, we can actually look at creating some classes, some objects that start to create a linked list for us. The first object that we'll create is a node class, and it has data, and it has a pointer to the next object in the linked list. And here we have a constructor. The constructor takes a data and stores it, and a constructor takes a pointer to the next object with a default value of null, and it stores that in the next object. Once we have this node defined, we can actually define a linked list class, and the linked list class would have a pointer to the first item in the list, and here we have methods for inserting an item in the front of the list, and a method for computing the size of the list, and a default constructor that sets the list to null. So let's assume here is possibly a main function, and it creates my list. The default constructor would set P first to null. If we were to immediately call size, P Walker would be equal to P first, which is null. P Walker not equal null would fail, and we'd break out of this loop, and we return size, which was initialized to 0. Well, that makes sense. We haven't added any items to our list yet. Here we insert front a value of 5. So what that does is it creates a car in the train that has a value of 5, and by default a null next pointer. Then, and this is going to be pointed to by first. So again, we've got, my diagram is disappearing. Then the next thing we make is the 10, and we put the 10 here, and it's going to point to the next guy. I can't draw fast enough to keep up with it. And first is going to point to the 10. So if you look at the code here that inserts the front, the idea is that we make a temporary node, and the temporary node has the new value that we want to make, and also has its next pointer set to the same thing that first is pointing to. And then we update first to point to this new node. So that inserts into the front of the list. If we wanted to insert into the back of the list, we would have to loop through all the items until we reach the last one, and then add the new node to the pNext pointer, and that would put it at the end of the list. So it really would be a good exercise for you to code this up, create a few diagrams, write a function that would insert into the back of the list, and test it out and make sure it works properly. Very good exercise, and we will do this in the discussions this week, and so I encourage you to reply and post what code you get for creating some of these other functions. And here are a list of methods that may be useful to add to our linked list. The first one would be to convert the data to a string. So if it's just a collection of numbers, you may create a string of those numbers separated by commas, or print them or display them on the output. We talked about inserting into the back of the list, so you would loop through the list until you find the last node, the one that has that sentinel value in the next pointer, and update that next pointer so it points to the new node with the new value. That would be inserting into the back of the list. Removing from the front of the list, so you have a temporary pointer to the thing in the front. Update the first pointer to skip over it to the next one, and then free up or delete that temporary pointer, and that would be removing from the front. Removing from the back is similar, except you just have to find the last node and free up its next pointer and set it equal to null. Clear or delete all. So this is interesting. We already have a size method, and because we have a size method, and assuming we implemented one of these, remove front or remove back, we could then create clear all with just a couple of lines of code. We could say while the size of the list is greater than 0, then call either remove front or remove back. The value exists, so this value exists function would be similar to what we saw in the bag class in previous work, where we would search through the list to see if a particular value is found in the list and return true or false. So that's just a matter of doing a traversal, and if we find a value that we're looking for in the list, return a true. If we get to the end of the list and we haven't found it, then we can return a false. We can remove a specific value. So again, we search through the list, we find a particular value, and we have to create a temporary pointer that points to that node, update the pointers so that that node is removed from the list, and then delete that temporary node pointer. So you can come up with a lot of different methods that you might find useful in a linked list, and what I'd like you to do is to take one or more of these and try to implement them, test them out, and reply back and share the code that you came up with for one or more of these methods. Finally, another comment to make on this linked list is that notice that all the pointers went in the same direction. They're all pointing to the next node in the list, and that makes it easy to traverse the list in one direction from beginning to end, but it makes it also very challenging to traverse the list in the reverse order. What if we wanted to go upstream in the opposite direction of the pointers? That's a very challenging thing to do. So what they've come up with is the idea of what's called a doubly linked list. So in this case, we have a singly linked list where each node has just a single pointer. A doubly linked list would have a situation where the node has two pointers. P next, just as we've seen, and also P previous, which is a pointer to the one on the left or the previous node in the list. So in this case, the P previous, I'll just write prev, this would be a null value because there is no previous node in the list. The P previous here would point to this one, and the P previous here would point to this node. So now we have nodes that have pointers to the next node in the list and a pointer to the previous node in the list, and you can create a first pointer and you can also create a last pointer. Add that to your list class, and now you can traverse the list from head to tail or first to last, or you could traverse the list from last to first in reverse order. And so it's not uncommon, if the application needs it, to have a linked list that can be traversed in either direction. A final comment to make on performance is the fact that an array implementation of a list container, because it's an array, the traversal is very quick because all the items in the array, even if it's a dynamic array, are contiguous in memory or adjacent in memory. In the case of a linked list, because these different nodes were created at different times, they may be spread out in different areas of memory, and the traversal of the list may be a little bit slower than that of a dynamic array implementation. However, notice that when we add an item to the list, so if I want to insert an item on the end of the list, all I have to do is create a new node and update the pointers. In the array-based implementation, when we wanted to increase the size of the list, we had to allocate a new block of memory, copy the memory from the old block to the new block, and then add the new item. That creation, and then delete the old block of memory. That creation of the new block of memory and copying can be expensive when the lists get very large. Here, to create a new item for the list, it's just a matter of creating one object and updating some pointers, and that's very fast. So a linked list implementation has the advantage of being very fast in adding and removing items from the list because the resize doesn't involve an allocation of a second list and copying. However, the traversal could be a little bit slower because the nodes in the list were created generally at different times and might not be adjacent in memory, and so the traversal may be a little slower. So there are trade-offs and advantages and disadvantages of array implementations and linked list implementations, and depending on the application you may decide to choose one implementation over another. So I hope this was a good presentation for you on linked lists, and I look forward to seeing your replies in the discussion areas.